kinetics, you start with balanced equations. Equilibrium, you start with balanced equations. Stoichiometry, you start with balanced equations. Why? Because it's chemistry, that's why. Things react. Of course. So the starting point for anything you do in chemistry is to write a balanced equation and work from there. Now, when we start talking about the equilibrium expression, it comes directly from the balanced equation. And it's always products over reactants. That's the first thing you have to keep in mind, because people always get that upside down in the middle of the semester even. So I'm going to do this in concentration units. No plus signs in here, it's multiplications. You're always doing multiplications. Raising things to power is essentially multiplying a bunch of times together. Okay? Anything else in the product side goes in there. Then you're dividing by. Anything in the reactant side goes in the denominator. And those coefficients are the same as the exponents, or the exponents are the same as the coefficients. This is what we did for elementary reactions also. Okay? So the first part is to write the equilibrium expression, and we use square brackets for concentrations. And this is referred to, in general, as being equal to an equilibrium constant. Now it's constant as long as the pressure and the temperature don't change. Or if you change the temperature, you can change the value of this number. If you change the pressure, you can change the value of that number. So we'll look at some of those effects later in the semester. But right now, we're just assuming, I guess, that the temperature is staying constant. That's what causes the biggest change. Although we can express, and this little c denotes different things. In this particular way of writing, it just says we're working in concentration units. I can talk about K sub P in pressure units. Now the equilibrium expression would be written in terms of pressure. We could have gases and solutions together, and then we'd have a mixed equilibrium constant. Fortunately, we don't do any problems like that in Chem 1B. So I'm not bothered writing it, but you realize we could write, and when we get to thermodynamic equilibrium constants, we'll refer back to this again. But all of our problems that we're going to do are mainly in terms of concentration units. A few of them will be in pressure units, and of course, we'll get to the relationship between K sub P and K sub C the next time. Okay? Now, the first thing you want to do is write the equilibrium expression from the balanced equation. And here's the thing. We don't include certain things in the equilibrium expression. We don't include solids and pure liquids. Sometimes words they use is neat, N-E-E-T, liquid. Now, I can't spell pure, so I'm just going to say liquids. And I'll rationalize that in just a minute. So we don't include solids, liquids, and when we get to acid-base equilibrium, we won't include the solvent. And we'll that's for a specific case, and we'll look at that. So solids, liquids don't go in the equilibrium expression. Solvents, when we get to the part where we're going to have different types of solutions, we don't bother putting the solvent into the equilibrium expression. Okay? Now the reason we don't put these in, notice the square bracket refers to the molarity or molar concentrations. That's the same thing. But we don't, that's not what's supposed to be in there. From thermochemistry and things, what we should really use the activity. So we talk about the activity of C, the activity of D, activity of A, activity of B. Unfortunately, you have to go through another year of chemistry before you learn how to calculate activities. So you use molar concentrations to calculate activities. But the conclusions we're going to come up with doing this will be pretty close, will be almost the same. That's why your book sort of rounds things off to 1 or 2 figures. And when he does his equilibrium problems, and I like to see 3 or 4 so I know where to look for mistakes. So that's a different reason. But what happens is, when we talk about activities, one of the ways of describing it is it's the effective concentration. And the reason we get away with using molar concentrations, at low concentrations, the activity number, and notice it's a number, it doesn't have a unit, the activity number is equal to the number you get for the molarity. With no dimensions. I'll put a little squiggle there, approximately equal to the molar concentration. Now the big difference between molar concentration and activity, we can talk about a 15 molar 12 molar HCl solution, or 16 molar nitric acid solution. But the largest number you get for activity is 1. You cannot get an activity higher than 1 because it means it's there with full effectiveness or reaches its maximum value. And the activities of solids and liquids, since they're pure, there's nothing diluting them out, are 1. So for solids and liquids, and I'll just write one of them equals 1. That means if you put 1 to the 5th power in this expression, what do you end up with? 1. So you don't bother putting it in. So when there's solids or liquids in the equilibrium expression, I just put solids, but that's also true for pure liquids. The activity is 1. Then you don't bother putting it in because raising 1 to any power is still raising 1, and it doesn't affect your calculations. The only thing that has to be true is if there's a solid in the reaction and there's no solid present, then you can't have an